Okay. Coming to support vector machine, this was definitely the before deep learning and all this came into picture for classification of really uh, you know uh, data which is more entangled with each other, which was difficult to separate with logistic regression with earlier known techniques. SVM played a very important role over here. Separate data which was otherwise difficult to separate out based on the modern stuffs. I mean, based on support vector machines. Mm. Okay. So that was one thing. Okay, so you have your traditional classification technique like logistic regression is there, naive Bayes is there, decision tree is there, but beyond a point, I mean, if the data was too much of entangled, it found it was difficult to solve it using them. Okay, that is where SVM come into picture. Okay, so there are certain important high points about SVM, how it solves the thing. Okay, and one important aspect about one parameter, that is kernel here. Okay, we will configuring the kernel part in SVM. What happens using that, and how you can use SVM as a linear regression also to find a polynomial line. You can use by changing the kernel also, right? You can change it to create a, like if you have a data which is inside data is all yellow, outside data is all blue. So what will be a separator? A separator will be a circle here, right? What you're trying to say. So in linear regression, you have to, I mean, if in logistic regression, you have to find the separators by various trainings. I mean, degree 2, degree 3, and all that. This guy can do it directly. Okay. So we'll see what I'm trying to say here. Just to understand, SVM can do a little more complex tasks as far as, I mean, people used it for a lot of years for doing image classification as well. Okay, people thought they could solve this problem. So SVM has higher respect compared to other guys. You can use the concept of SVM for doing few more things. That is for doing regression, also SVR for vector regression. You can use for classification. That's for vector as we see. Right? You can use. It is supervised.
So for logistic regression, it uses only the 1 degree, like it will classify in terms of separator would be a line or a hyperplane.
Right. And then you can pass a polynomial data and make it
plane, like one particular wall. Line will be a single one dimension, that will be 2 dimensional.
And more 4 dimensional. Suppose your data is a 2-dimensional plane line data, so you have to create a plane which separates the data basically. Okay, I mean 3-dimensional stuff. Then you have to create a plane. It is 4-dimensional to create a 3-dimensional. I mean that beyond that it is all called hyperplane.
Okay. So all the naive-Bayes, Gaussian, all this uses the same thing. No concept of any degree over there. And naive-Bayes or Gaussian.
Naive-Bayes there is no concept. I mean it uses a probabilistic model there. Similar decision tree uses a concept of Gini and entropy, right? It basically generates the question. Right, and it uses entropy of the separated data to identify which class does the data belong to. Okay, so that is all around these techniques. Now let's see SVM and why SVM is a little different ball game. Okay.
On which mathematics it is based in? Mathematics.
It is actually based on this mathematics itself. It is based on your what do you call this, linear algebra itself. Okay, some derivations of linear algebra, but what it does here, it does things little differently. Let me show 1 or 2 diagrams
here. Like in ML, they use a lot of statistics and probability. So in DL, what type of mathematics is required?
Here same.
Linear algebra I have not seen.
No, in deep learning, no, it is used.
In DL.
Okay, so just let me give some examples. No, that is calculus is there in your. It is the mathematics is also. I mean, there also you will have gradient descent, whatever you have discussed here, right? There also you have gradient descent. There also you have back propagation. For back propagation, you use differential calculus. I mean, how the information is back. The chain d by dx of chain mathematics, right? That happens for differential calculus. Okay. So mathematics wise, whatever you need for machine learning, you need same thing stuff for deep learning also. Little more than that. Okay, so what am I trying to say here is, let's just check out this diagram. You see this diagram. So suppose you have these two data sets, right? One is your yellow and one is your black. So that's red. One is your yellow and the other one, right, dark color. So what is the best line which could divide this? Why? What makes you think so?
Because separates, it's maintaining much more distance.
Right. And how are you doing it? You're doing it based on some support vectors, basically. You're taking this decision based on the vectors which is the closest here, isn't it? Right? These are known as support vectors. Okay. So unlike our previous algorithms, which is based on all the data set, here support vector machine is based on the support vectors only, which is basically closer to each other. Okay, and that is why it uses. That is what actually.
This is 3D and 2D.
It is 2D data. Okay, and what you're doing, 2D, the data is 2D, right? So you need a n-1 plane to divide the data. Understood this line?
No.
The data is 2D, but how is each data represented? X and x comma y. So what is the degree of the line that separates the data? Degree 1. See, degree 1. If you have 3-degree data, right? If you convert a data to 3 degree, then what will be the degree of line which separates the data? This is the most important thing to understand in entire deep learning, machine learning, whatever it is. Okay, this is known as polar coordinates. You can note it down later. It's known as polarizing coordinates or polar coordinates. What is it doing? It is actually converting that's essentially the game, right? You have data. You basically need to convert the data into a dimension. Okay, and you basically need a degree of plane to separate the data. Right, that's what you do in machine learning. That's what you do in deep learning. So that is where representational format. Okay, so here
polar coordinate.
It is the whatever we mentioned. It is the idea of See, what we understand is if your data is like this, you can definitely create a 1-degree line which separates the data. If your data is in 3 dimension, what will be separating it? Plane will be separating it. Right, a line with what is the equation of a plane? Equation of a plane? Nahin. That is the equation of a line.
Okay.
Ax, by,
that is good. That is equation of a plane, right? So that is why, if you remember, when we talk about logistic regression, okay, when you have multivariables, what was it generating? It was generating a equation like ax plus by plus c is equal to this, right? What is that? That is actually a plane. And what is the dimension of the plane? One lesser dimension than the dimension of the data. Right, that was the thing around it. That is one lesser dimension than a dimension of the data. So similarly here also. So that is the entire game that we'll play now. Okay. Now with this, a lot of things we did it with this. All of things, more things will converge. Okay. Why this is why it was that case. Okay. Okay. So. So in this case, what will SVM do is SVM will find what are the support vectors. That is the first thing SVM algorithm does. It will find what are the support vectors. Right. In this case, it will find the points which are closest to in the training data itself. Right. It is closest to the other class of the data. That may be little messed up. Whatever is it. Okay. Then what it will try to do? It will try to find which is at the best distance from both of them. And in this case, if you apply SVM, so if you apply logistic regression, your winner can be this, anything, right? In SVM, your winner will be invariably this. Got it, right? Huh? Okay. So that's what the cause is. So if you have the data, and let me see if I can plot it. Okay, if you have the data, if you create a logistic regression, it can be this line or this line, or this line also it can be. Okay, but if you're using support vector, it will be this line, because this line.
How do we decide when to use SVM instead of logistic?
So basically, SVM will be using it more often when you think logistic regression is not
So you also had that SK learn that one diagram, right?
Exactly, that can be the point. We can see that.
And how do we identify logistics and personalization working?
Accuracy. Okay. So
In that case, there might be a point like, say for example, every time we train the model, so we get a different kind of score.
that is why your training and validation has to be robust. And if you, I mean, you have to rely on those numbers, whatever you're getting. So you can use cross validation, right, to see if you're getting a robust answer or not. If it's like here, right here, if you see
one of the exercises should be you should give us 20 problems, and looking at this, you should just ask us to say where we should use code. I think that will clear most of the things. Correct, where to use code. Because that is the crux of issue already.
Understanding when, I mean, how to approach a problem, how to approach particular kind of problem.
This one is very, as in, I thought this was one of the best ways to look at, at least in case of machine learning.
It's under regression as we are.
Okay, so here you can see SVC here. So you have tried with naive Bayes, but linear SVC is very simple, similar to your logistic regression, right? Here also just remember SVC can work as logistic regression also. That is what linear SVC is. It is just basically trying to find a plane. Remember, this linear word does not. I mean, I think this we have all understood. Linear word does not mean one line. It means at one point of time it is linear. Okay, that is what it means. Okay, so you can see here, you get this data. Okay, so just think of, I mean, before you get this call, what to use. You will use, I mean, you will write that class. I think we wrote the last class. I think we are writing classes, right? And using various algorithms, you'll see which one is working out well for you. Okay, this is the fundamental thing you have to do. You cannot, before even executing it, you cannot have that notion that it will not work for this.
No, but this gives me, right, if my number of categories
this is a very high level information. This is not way, you cannot use this to prove anybody that this has not worked for you.
No, but our initial set of things, I'll not use the whole world for all the problems and then see which one is working. There has to be some way to first narrow down, right? What 5 set of things I'll be using for 3 set of things.
Yeah, I mean, you'll start with a benchmarking case. If it is a classification, we'll start with logistic regression to see what is it doing it. If it is a linearly separable data or not. Okay, if there is outliers or not. I mean, we'll use that as one of the technique. Then you'll going forward. And as you see here, linear SVC. This means it is similar to a logistic regression. Okay, so this is definitely one of the starting points. Okay, then if it does not work, you have SVC. You have ensemble classifiers, right? So linear regression is a starting point. You can go to naive Bayes after this. You can go to ensemble classifiers. You can go to SVC after this. Okay. Okay. Then of course this is another data set. I mean, this is good for smaller data set cases also. Okay.
So SVC here is
support vector classifier.
And SVM?
Support SVM is a broader category. It consists of SVR and SVC. You can see here.
Yeah.
You'll have SVR.
Yeah.
Right? This is for regression.
Back to the water bottle.
No. It's hidden. Hidden layers. No. Green. You can see a red.
On the green screen.
On the green screen.
This one?
No. Yeah. Hey, why is the AC not working?
It's working.
Yeah.
Now we can see something like that. From our angle, it was not visible. He knows also.
Of course.
Yeah.
Okay, so let me generate some data. Let me generate actually blobs, circles. Okay, from sklearn. Make circles. Okay, so we'll try to generate circles out of this. Okay, so and we'll see various types of SVM. What are they trying to do here? Okay, understood. Right? First point, it uses only the support vectors. The first important task that support vector machine does it identify what are the support vectors. After that, it uses only that to identify the separator here, and there can be multiple separators. Okay, so let's see what happens. You have multiple separators. One separator means you have one very similar to your logistic regression. We have one plane here. You can try various options here. We'll see various options of separator and what is their accuracy. Okay, and why it is good for the data which is not so easily separable. Make circles. Okay, suppose you have 100 points and you have noise is equal to 0.1. Okay, so let's first plot the data. Percentage.
What is noise?
Noise is will generate the data, and how if you don't mention noise, it will be a perfect circle.
And if you mention it,
and we want the features also, right?
What is making 0.75? Lesser the numbers, is it better?
Lesser the point of which a noise. Noise means it is closer. If you add more noise, it will be a little distorted. Let me just show the data, dump the data. Actually. Okay, so we have, so see this y value. Y value will be 0 and 1, right? And x value will be, remember, 2 coordinates. Okay, I want to plot it now. ELT dot scatter. Okay.
why is 2 values? X means what?
X means see y x is that is a data point. Each point is represented by x and y, 2 data point. Okay, this is your first data. This is your second data. This is your color is equal to y. S is equal to 50. C map. That's okay. Did you notice this now? Okay, we have to create a separator for this. You can see noise means if you increase the degree of noise, it will be more jumbled up. If you don't write the noise, it will be a perfect circle. Got it, right? What is noise? Okay. Okay, so we have to separate. Just imagine these are 2 classes of data. Understood, right? 2 classes, and we are trying to find a separator between them. Shall I try logistic regression? See what is the accuracy? Okay, so it will basically, I mean, with degree 1 it will not work. Okay, with degree 2, what will be the best degree to separate this data? Degree 2. What is it? Circle, right? What is the equation of a circle? Right, right. So that will actually separate. A circle is the best figure which will separate this data.
But
right?
you said for 2-dimensional it will be n minus 1. Then it will be straight line.
So this is 2-dimensional data, right? So can there be a straight line which is separating this? No. So what will you do? This is the case. You'll add one more dimension here. Or thinking wise, if you plot this data in the 3-dimension, then you can create a plane which is separating this. What will be the equation of the plane? It's a 2-degree plane. That is your polar coordinates. Okay. So let's see it. It will be clear. Okay. Okay. Now, let's first try to separate it with degree 1. Okay, so from let's.
So normally in a data set, if you receive a data set, large data set, so are we supposed to find a separator by using SVM? If you're using SVM, let's say if I get a.
You basically want, yeah. If you what do you want out of this? You want, if you will give a x and y coordinate, it will tell you it is class 0, class 1.
Correct. But I'm just trying to think, when I get a data set, in that data set, if I'm planning to use SVM because linear regression score is not working well, I need to have a separator, right? In the data set.
Right.
That's mandate. There is no other way to do SVM other than having a separator.
No, I mean SVM is a classifier. I mean, you are using as a classifier. Okay, so that will be the separator there, right?
Okay. Without having a classifier, there is no other way to use.
And SVM is good for imbalanced data. I think somebody, hey Mohit, you are there? Mohit or yesterday someone? So yeah, we'll see how SVM handles imbalanced data also.
Okay, yeah.
Yesterday I told you, right? We'll discuss few things in SVM. So yeah, we'll discuss how SVM solves your imbalanced data. Let's first understand things around it.
Yeah.
Okay, and okay. So anyway, we understand linear logistic regressions. 1 degree won't solve it. Okay, when we won't get to, I'm directly doing it 2 degree and see what is the result. Okay, since we know I mean, this we can do because we know the stuff, right? I mean, let's see. So polynomial features. From ZekeLabs. X comma y. Right? I've broken down the data. Okay, and basically I should be doing it after first step. Okay, X is equal to Paul dot fit transform X. Right? So what will be my train X? Train X shape. Fine, right? Y is 6, degree 2, x square plus y square plus xy, x and y, it will be total 6. Fine, right? Our initially the number of columns was 2, now it has become 4 here. I mean 6 here. X square, y square, xy, x and y and plus 1 coefficient. 6. Right? So let's use linear logistic regression from ZekeLabs dot linear model import.
It shows one more, right?
CV, wherever you see the CV, right, cross validation, you will take one more parameter. How many times you want to do cross validate, how many times you want to run this algorithm. and you can pass here which are the, like logistic regression has few parameters like C, capital C, to handle the randomness of the data. Right, it has one parameter C, it has one parameter reg parameter.
C is that bias too.
C, no, capital C, capital C. That is your linear. So here that is same thing. It's doing the same thing. Yeah, regularization stuff. Okay. So I mean, it will find the hyperparameters for you directly. All the CV functions that you see, right? It can find the hyperparameter. I mean, hyperparameters. So you have here logistic regression. Okay. Next thing that you are doing here. LR is equal to logistic regression. Okay. LR dot fit train X train Y. Bad shape. Oh, I think I wrote it wrong.
No, I think it's
right.
Small.
Here it should be test train X test X. Okay, train Y test Y. How I remember this is XX first and Y second. Train X test Y. Oh, train X test X, train Y test Y. Oh, correct. Right, now it has trained it. Now you want to see LR dot score to test X test Y. Okay, the score is 76%. Okay, it is a separator that is. I think this is fine. Okay, and if I reduce the noise, right, it is gone. That means it is actually predicting a circle for you. Got it, right? Degree 2. No, I just changed the data so that we can get a clear separator. Okay, so this is what is the logistic regression predicting you? Make circles.
You remove the noise.
I remove the noise. I set the noise to 0. Okay, so noise is actually the. So I just want to say absolute case. If you solve this with logistic regression with lesser degree or more degree, we'll see deviations from the output. Fine. This is what we did with logistic regression. Of course, to conclude this, we might have tested multiple degree of logistic regression, isn't it? Okay, let's see now how we do with SVM. So this is after. I mean, if you are trying to solve this problem, logistic regression, you use logistic regression degree 1, degree 2, and see which one is working. You see the accuracy of all of them, then you can conclude. That's how you do it.
So here we try to manually add a feature, right? And create a plane which can divide.
Yeah, that's what we did here actually.
So this was manual way.
Yeah.
So now we'll do it using the
SVM. Right. Okay.
Yep.
Now, okay. So as in SVM, we'll use a kernel RBF. So let's see this from sklearn dot SVM import SVC. Okay, now let's see. Okay, classifier is equal to SVC. Okay, here this is important. Kernel is equal to RBF. Okay, now it's few things to understand here. This SVM is actually takes the logic generation as an argument here. Okay, you have SVC kernel linear also. That is your linear SVC. Remember, right? This is nothing but your logistic regression.
Then we have classifiers.
So let's first see this. This is a logistic regression, and if you try to do this, okay, logistic is very similar. Degree 1 it will calculate actually. Okay, based on the path. Right? So
it's a default one. RBF is the default one.
RBF is the default one. Okay, but if you want, but remember, RBF means more computation. It will try with all possible degrees here. Here, this is the linear one. If I try to do this, we'll get accuracy same as logistic regression without degree polynomial. Okay. CLF.fit trainx train1 CLF dot score. train. Yeah. It actually calculated a degree for you here. Wait a minute. No, it calculated a degree. Which one? 3 default. He's using 3 as a default degree. Yes. This is your logistic regression. We got 60% accuracy, and if we give linear, degree 3 it is getting. Okay, this was the case. Okay, see this. Now, this is what I wanted to show. I think so you can see. I hope I've written everything correct. Huh? Correct, right? I'm not messing up with any classifier separately. But it's two rows. Yeah. So you can see here what happens here. So what was the earlier case? In earlier case, the data became little jumbled up here. Right? Data became little jumbled up here. And we are using this linear separator of this guy here. Okay, and what it is doing, it is of course, I mean, here you can pass more parameters, and here we can see it's almost the same result it is here. Okay, now just change one thing. Let's see if we can do that. RDF reduced, right? Why is it?
Bad noise.
I think we need to increase the data a bit. It's too less for it to be concluded.
Use data selection because the need place only.
Yeah, I mean the data is too less to.
I mean, during the train test split, whatever.
Yeah. It's too less. This can be a good data, right, to understand this. So here, regression and the score is 97%. This is a degree 2, and here, okay. And if I use linear here, it is getting close, exactly same as this guy, right? It is much more. Linear is same as linear regression. That's what, right? Linear SVC.
I actually got the same for I got the same value for
Not getting the right observation.
Simplicity test split. Probably, yeah. If you still increase the number of data points,
you can try running
and
that
make the noise more, right?
No, not this. Say running the train test split.
Test split.
because linear was not supposed to give so good result actually. It is.
I got 71.
So,
I got 71.
Yeah. Okay. So what you see here is this kernels, right? When I mentioned linear, RBF, okay, and there are a few more kernels. Okay. So each kernel now using this different kernel, what you're telling here to do more things. I mean, generally linear is similar to a logistic regression. You're trying to find a plane.
What is a kernel?
Kernel is the external function that you're providing. Okay, that is what makes your SVM very much configurable. Okay, so what you can do, external function in the sense there are few options here for you.
So I think two things important over there. One is that what is the linear that we saw?
This one linear.
Yeah, just go a little bit up, scroll a bit. There is a solver. What is that?
That's a logistic question.
A logistic.
Here it's this guy, kernel linear.
Kernel linear.
Yeah. So there, yeah, just I'm showing it.
And what is decision function state? OBR.
These. Somehow not showing what I wanted to show. I need more.
So it's definitely not the data because you try to increase the data set.
Right? Still, I mean,
not.
Split that's happening. Because every time you do split,
no, I didn't execute split here now. I just changed this, right? Split, I'm not doing split now. Okay, wait a minute, wait.
You can change the degree, right?
Okay, guys. I mean, that is the reason. No. The reason why this is behaving this way is because I should not have done the transform. I'm using transform data for my SDC. See here, right? I should have used directly. That's what the results are not. I'm transforming the data. I'm using it for logistic regression rate, but I should be. So here onward it will change, right? I should not. That's what I should not be using. So you have this trainx underscore SVC underscore S. I'll copy the whole and just change. Got it, right? So. Yeah.
While again you're given the transform data only, right? X will take the
no, X and Y is not transform data.
Yeah, it is. X you have been given fit transform as
X.
You have given in the same variable.
X equals to 100,000.
Oh yeah.
So you need to change it from here itself. You need to assign some other variable.
You assign some other variable.
Same thing you can copy, right? On top. Wherever we had X by equal to make circle. Just there. 109. You're right.
Yeah.
This point. No, इसके भी ऊपर कर सकते हैं ना.
Oh, that's okay. So here I have to change in one place actually. As L. And here. So my X is intact now, right? So this will be the outcome for my logistic regression. Here it is intact. Doing this, and here it will be trainx. Actually, I should first start with linear.
Okay, minus X.
Okay, so this is with linear separator. Okay, now just change it to RBF.
No, it's not doing the same value. Data is changed again, or you?
Data is same. Data is
not doing the same value. So,
linear and this one. Here it is just. So now you see. Now we should see much improved result. Yeah. So what is happening here? In linear, when you mention linear, okay, it is just working. I mean, of course, this is whatever 54 or when it's 54%, right? So if you use logistic regression with a degree 1, it is same as linear. Got it, right? Logistic regression with degree 1, where you're not doing the transformation of the data, it is same as degree 1. Now this 84% is same as, yeah, now this is same. Now what is the thing here? So in earlier case, you did the transformation to degree 2, right? Then you apply logistic regression. Two things you are doing. In SVM, now with RBF, what is it doing? It is finding the right,
degree as in
right plane which can separate the data without actually you doing the transformation part. Right? This is what is the expected of. You don't have to go through the process to identifying the dimension and all that. This is because this you have suddenly short circuited the entire thing, right? Okay, let me just repeat what we happened. We apply logistic regression with degree 1, say. We'll get something a bad accuracy of around 54% if we apply. If we apply with degree 2, since the data is in circle format, I mean the separator, it degree 2 worked out it will. Just imagine n-dimensional data, right? So you have to manually do those steps and then you have to get there. Okay, so that is one way by which logistic regression is solving your separator problem. What happened in SVM is basically you are not doing the transformation part, right? You are not converting. See, our train X and test train Y, if I dump the data, it is just 2-dimensional data here. Right, 2-dimensional data here. We are not doing the transformation. So how is it doing all that? It's not that it is combining both the things and doing it. Its principles here are different.
So the transformation is inbuilt.
No, that's what. It is not doing the transformation.
Correct, but
how it is doing it, right? Yeah, that's what I'm coming to.
In the previous case, we are transforming the data and then we use it. And later on, when using RPF, we are not doing anything at all.
And you can see the linear thing is similar to.
In this example, we have already done it, but ideally we won't have done.
Which example?
Yeah, we have made it, right?
Yeah.
Later, logistic regression.
This example that you have. But we are not applying that in this.
In SBC, this data, right? This is the actual data. It is not transformed data.
Yeah.
Right? This is not the transformed data. So what does it mean? I mean, you don't have to consider. It is pretty closer to your deep learning, isn't it? I mean, the philosophy is okay. There in deep learning, you don't actually have to do the transformation, right? I mean, degree 2, degree 3, it is able to calculate. Here also, you don't actually have to do it. How it is doing it then? Is whatever we did so far is clear? Right? I mean, I'm just comparing with logistic regression. In logistic regression, what you're trying to do is basic logistic regression won't work. You did a feature transformation to degree 2. That has worked and given a good result, right? For a very simple data set like this. Now, just think of more higher dimension. So you have to take care of, and what you do, you will have to find which is the best degree by converting all the degree into. But as the data progresses, whatever your derived features is, as the number of columns increases, what will happen with degree 3? We'll be talking about 170,000. If you have 100 columns, if you're taking 3 degree, what is the total number of columns in that case? 170,000. Okay, I mean, I know the numbers, so 170,000. Can you do machine learning on 170,000 columns? Of course you can, but not realistic. It's too much. 170,000 columns are too much of sometimes to do. That is where SVM comes into picture. You don't increase the number of columns. That's what doesn't happen here. Okay, it's not that it is internally doing all these things to you. No, the philosophies are different here. You do not convert your data to these many degrees. What it does here, using this RBF, it tries to represent your data in higher dimension. Then create a line, find support vectors in it. So first, let's understand the first meaning. What is representing your data in the higher dimension? Suppose you have data in 2 dimension and it is little jumbled up, as in this case. Just imagine it for a moment. You have this data mixed up. Okay, what you have to do here, okay, is basically if you try to bring all the yellow data, I mean, if you just try to convert this data into 3 dimension and you try to bring the yellow data little up, can you create a plane which can separate the data?
Yes.
That's the thing that happens. Okay.
And slice it off.
But that's it. Yeah. So that's what SDM does here using RTF technique. Okay, that's why it is able to separate data which is generally not so easily separated. I mean, so but you can still do that with logistic regression.
By doing that, so you're saying I'll be raising value of one of the coordinates for all the data.
For all the data. So what will happen? You know that this. I mean, you'll find. I mean, that is what SDM does. It will find. Okay, these are the points. These are the support vectors. That means these are the points which are messing up with each other. Then you, based on that, it will add dimension to all the data. Okay, such that yellow data comes up or the purple data comes up and the yellow data goes in, and thereafter you find a plane. The thing is, just compare it, and the reason I gave logistic regression example. Just compare it with logistic regression. Say you can of course do this with logistic regression, but what happens? The number of columns after you do polynomial transformation explodes. Right? That is why you cannot do with logistic regression after a point. That is when you talk about images. What is number of features in each image? Number of pixels. Right? Number of features in the image is number of pixels. So think of the number of, why cannot you do that with logistic regression? Why can you do that with SDM? Understood, right? Why, when you take the decision making, what kicks in here?
Number of features.
Yeah. So logistic regression, cool, but you have limited number of features.
One thing I just saw one thing. Actually, you're using mixer for 1,000 right now. I had it up to 100, and RB was actually performing worse.
Yeah, because I mean, as for a smaller data set, it is.
Better.
I mean, 100 data set is actually not a qualifying data set for deep machine learning. Okay, I mean, most of the things will not give CM. That's why I should have it. So, but anyway, I mean, yeah.
I actually just observed that because we are giving a score of around 65. While logistic regression was giving.
Yeah, SVM needs more data. Okay, I mean, having said that, if you have lesser data, lesser columns, logistic regression is good. If you have more columns, more data, lesser column, logistic regression is okay. But if you have more columns or more features and more data, SVM is better.
What about overlapping data? Overlapping data, then neither of them will work.
Yeah, overlapping data is basically I mean, in this case, for example, that yellow is there in middle of red, right? Okay, that. So when you separate it out, okay. So what it SVM try to do is try to bring as much as yellow data down and up. Okay, that is the training data set. If I pass it in the training data.
Why do you say that? Overlapping data. Okay. Like, I want to understand what kind of algorithm that we can apply. Like, decision tree would be a better option, right? If the data is too jumbled up and classifier won't be able to resolve that. Yeah, you cannot classify. Here you can see there's a kind of separator that can divide the data. But in that sense, where a lot of overlaps data, then classifier won't be satisfactory enough to resolve it. In that case, what do? We do decision tree or some kind of forest and separate techniques.
Ensemble technique is good for when data size is smaller.
And data is smaller.
Or relatively smaller. It's not that huge.
Okay. But as he says, will it not work in overlapping? I thought it will work better in overlapping. Right?
No. I mean, I didn't hear that. I just heard that part of the question where you said, random forest will work or not work.
Okay. So I'm just saying when the noise is more. If you can increase the noise, what would be the result? Because the data would be more jumbled up and messed up, right? So there won't be a proper classifier. But then the idea was that all the yellows you bring up, right? But even if you bring up, then the blue ones will also come, right?
It will at the top and the blues are at the bottom. So is it separating that properly?
Yeah, exactly.
So if this is the case,
if you're pulling it up, you are taking a center point and you are just fetching it up.
like this. So it will be kind of conical structure that will be created. If you can visualize, then all the blues will be on the upper half of the cone, and all the dark ones will be on the lower half. You just slice it off in the middle, right? Now,
but you're saying only with 3D.
Yeah.
Okay.
Now you consider it
remain only in 3D.
Huh? Because that's the data. I'm just talking about this particular scenario.
Okay, so I mean, coming to that. Okay, so of course, if you say that you are separating the data, okay, when you are doing that, the algorithm, right, needs some data points, needs some information, which class is it. Of course, it will not be able to separate all the data. It will try its best based on this algorithm. Okay, it works to a certain extent, but if your data is, I mean, too messed up, I mean, data points, then you might have to work more on the data cleaning part as well.
More of the, should we keep in mind that overfit or more generalized use case? If it's overfitting is happening or is it generalized?
It is more generalized.
No, I mean, shouldn't we keep that in mind as well when we are trying to fine tune the algorithm?
That is where your score function, like here, I have actually added more. I added more. See, added more noise. See this data, huh?
Then the structure, that's what I'm meaning. Even then the structure that will be created, it will be something like this.
But it won't be one circle itself, right? If there's stairs up in center which are come up.
Then how do you define a one single
No. See,
slicing off?
Let me. There is some misunderstanding that. So definitely, we try to separate the data. Okay, but it of course means that you have to. I mean, when you're separating data, you will be applying a logic, right? Okay, if x and y is this parameter, then add this parameter. Some logic. So this logic will be generalized, and of course, it will not work for all the data. Like in this case, I increased my noise. This is important point about using decision tree and all that. It shows very good what do you say, overfitting situation. I mean, it doesn't overfit so easily as VM. Okay, that is what. See, in the training data, I've just increased more convolutions. It's very messed up now. In training, okay, you can see the score part of it. It is trained data score itself. It is giving 68, and test data is also it is giving quite competitive. Right. So when it is trying to separate the data, then also it is doing it based on some logic. And of course, a lot of data falls under this logic. At least it tries to, but not all of them. So there will be, the separation will go bad if the data is too convoluted.
So in that case, decision tree.
Yeah, in that case, see, if the data is too messed up, maybe you need more specific thing. Decision tree can work out for you. Can. Okay, you can see the diagram. Okay. So, but
create the more kernels, right?
I can.
Something mentioned in the cycling document.
You mean what you're talking about? Adding more dimensions to that?
No. In the column it is used to pre-compute the kernel
documentation, no?
And it will bring up all the spares.
So I mean, we are about to see more things in it.
So when it will bring up all the spares upright, which are supposedly yellow or blue, it won't bring up that would be ideal. Because I'm cutting off the system. So whatever are the islands which are for the data, they are left down. But in that case, you are just putting one data up, yellow data up, right? But then you don't know which is yellow and which is red. How would you know? That's how I'm in my trading. I have that already. But generally, how can you specifically say you gave a data or package over?
कुछ parameters है होगा तो हमेशा हर parameter match नहीं करते क्योंकि there will be some yellow points. Say for example, here I have the yellow points here. There are some blue points here.
Exactly.
So if I consider the coordinates from say even from the naked eye point of view, You will be confused that why are these blue points happening? Correct. So if I just try to take it out, I'll be confused that if I should consider these points.
Okay, so whatever generalized logic you generate to separate the data, I mean, basically are doing that, right? That is generalized logic. What it is try to separate the data, and this is not something that will work for 2 dimensions. It will work for n dimensions. Okay, n dimensions, n derived features. It will do for, you don't have to go the feature derivation and all that part. That is what support vector machine was good with image classification. But you know, data has to make sense. If you think the data is too messed up, that you better work on some more cleaning part of it, some pre-processing, get the data right. Okay.
Just show that algorithm where it was saying where I will be using SVM versus tree, right?
I didn't mention it anywhere.
No, you look at the scikit-learn, right?
Oh, no, here also doesn't share about it.
No, in your machine learning, you have the scikit-learn, the chart, right?
Oh, that's right. Here, so you can see here you have linear SVC. If I just try logistic regression, okay, and doesn't work, then try your SVC. Okay, if SVC, I mean, of course, here you have the option for ensemble classifiers, also random forest. So try with SVC, does not work. Try with random forest. So you have to deal with both.
First, I will try with one of these, right? And then I will move it forward.
Right.
Yeah.
Okay.
It's hard to visualize in that dimension.
Huh?
1 dimension, 2 dimension using visualize.
Yeah.
3 dimension also. 10 dimensions you cannot visualize.
It won't be visualized.
Exactly. So in that case, we need to be dependent on
This one, huh?
on the score accuracy, what each algorithm is giving. Based on that, we can provide with
each algorithm. The thing is, when I see that my accuracy is less, then only I go to the next one.
correct. But again, there is a chance for improvement in every algorithm. Again, there's a benchmark kind of thing. Even if you think for one particular
algorithm, this plot for 1,000. If there is 50 million data set, you'll be plotting and then figuring out what to be
not plotting.
Then how do you understand the data?
How do you know that you apply one particular algorithm, you get an accuracy of 90%. Now it's dependent on you whether you think whether it's 90% is really good or you want to make it further to 92% or 93% by applying some other algorithm. Right?
So that's some other algorithm you won't be able to apply if you don't meet those conditions. Right? That's why the flowchart is there, right?
We'll take a sample.
In classification, there are 4 to 5 algorithms which are available. Right? So you can apply all 4 and 5 and check, right?
So assume you're saying apply all 4, all 5. Assume you are running it on cloud. The cost of running each one is something like $10,000. Now what do you do? Right? Now do you want to keep on trying all of them? That's the whole thing, right? That's why you first have to do with first figure out, right, what you'll be using. It's not that you use anything, right?
So in that case, if you use 50 million data, so there's this case of sampling, right? In that case, we'll sample out the data and in which we'll see the minimal cause in which we'll be applying all these kind of algorithms. Not specifically all, but in that case, you will be able to understand that which all algorithm you need to apply.
In samples, some of the algorithms are supposed to be working better in less amount of data versus higher amount of data.
Now, so that's the assumption you need to. That's the line you need
no,
to.
That is why you do random sampling.
But you do that, but the thing is, you don't run everything, right? To say कि मैं ensemble में I'll run everything and then I'll pick up the rest, right? As in based on how much of a feature set you have, what is your number? That's why those things are there, right? I won't be randomly picking up 50 or 5 of these algorithms and always running them.
Not randomly picking 5 of this. First thing is we need to understand.
Actually, both of you are saying the same thing. Okay, I mean, of course, as you're also mentioning, there is a calculative approach, right? I mean, it's not that you'll use all of them. You'll have 5 contenders. Say in this case, you get number of columns are too much. Then of course you'll not try logistic regression for sure, right? You'll think about SVM and ensemble techniques, and you'll try to find among them. right?
The ensemble itself is multiple, right? When I'm running ensemble, there itself I'll be running 8 or 10 of them, or maybe more of them, right?
I mean, you will try one thing. I mean, you
ensemble the same algorithm run through iterations. But in case in another case, we can have different types of algorithms that we can merge together. So these are there in both cases.
Okay, so that's, I don't know where it stopped, and that's okay. Let's come back. Okay, continue. So continue after the session. So yeah, so here there are few more techniques here. Okay, first is linear, which is very close to as linear separator, trying to increase the dimension and do a linear separator over here, right? That is what your linear regression or logistic regression basically do. Then you have RBF. Okay, then you have poly. Okay, so let me take the next one. So this guy RBF will be using when the data is linearly inseparable. That means when the linear guy did not work, then you will be using RBF. Got it, right? Okay, so that is the thing here. If the linear guy did not work for the first data, we'll be using RBF, but RBF, remember, it works well when the data is between 0 to 1. So please do standard scaling before you apply that. Got it, right? Standard.
Is it possible to visualize that?
Which one?
The classification where it's showing like.
We can dump it actually. Here, what we can do is whatever line it is predicting, we can plot that line also. Not a problem. So we have this CLF, right?
That would be again some coefficients, right?
No, we can plot it. We'll use test text and trainers data. We'll plot it with different color. You can see that. Okay. CLF dot predict. Okay, this is your prediction. So what you will do? Will actually O will be 0 and 1, isn't it? Right. So what will you do? ELT dot scatter test x underscore s 0 test x 1 color, right? Color is equal to O and CMAP. I think forgot gray. I just want a different color. Okay. So it is, this is what it is predicting. This is the line. And this is from the outcome we are plotting it. Right. So if you plot, so this is the line it has predicted, isn't it? If you plot it with logistic regression, what will be the output? Why is it doing this?
Should be equal to color.
C is equal to
change, right?
Oh yeah. is OLR coming?
Instead of doing it on the transform data, you just directly do it on
transform data, right? Yeah. So what did I add it in? X, right? Yeah, I should do that. No, this is test X. This is your Y. That's okay. Too many indices. What is LR predict test X? Acha, because we have to predict it on X itself. To do again the data transformation. Yeah, these are the problems when you not do in pipeline, right? To do the transformation. But yeah, in that case, it will be little more shaped up here, right? In logistic regression. So what is RBF? RBF is good for separating the data which is linearly not separated. I mean, where your logistic regression would fail, this guy would, work out for higher dimensions. Okay, so what we can do is from the beginning itself, we have to execute if you want this. Train X, train Y is there, right?
So if you go at the plot, it's just a coincidence. Then you got the plot. Yeah, this one. I mean, it just seems that the white shape, right, is equivalent to the outer shape of the blue. It's almost similar.
This one?
Yeah.
Is similar to this one?
Yeah, the outer edges.
I feel to.
Key observation. Key observation. That would be what it doesn't look that similar.
Yeah, because.
But how does it matter? Like, what's the point?
It has to do with data generation, nothing to do with. I mean, whatever algorithm it is generating, same noise, same data. So I think when I do to that, yeah. I mean, if you look at, there is some similarity. Cannot say no to that. Okay. Okay. So once you do this, right, you can predict the support vector also. You can just try this. All you have to do is just change the plotting part below, right? Just make sure those variables are same, the sizes, dimensions, and that. Okay. Just avoiding this for now. Okay. So if you want to know what are the support vectors, so I think what was my model name? CLF, right? CLF dot. You'll see support vectors. You'll find the points which are helping to decide it. These are your support vectors. CLF dot support vectors. How many support vectors are there? 5,330 support vectors. Okay, got it, right? From the entire data lot of how much was it? 1,000, 10,000, 10,000. From 10,000, it is taking 5,000 data in deciding. So data is really messed up. If you really have a clean data, for a circle data, it will always be, you have to find those points where you have to find the separator. This is the separated points. If you have a data which is linearly separated, you will basically have 2 support vectors, 2 or 3 support vectors. Understood what is the role of support vectors here? Okay, so basically if you have a circle data, so the points will be all these points which are eventually deciding what are support vectors, and it's good idea to plot those support vectors actually. S colon comma 0 S colon comma 1 size of it 50, right? So these are the points which actually decided the separator in the whole data.
What is this S equals to?
The size of the point. If you give 0.5, then it will be very small points. These are the support vectors here. So these many points contributed in making decisions here. You know what should be the shape like.
So size and scale.
S is size of the point. If you want much more granular information.
The count of the points will increase.
No, same.
No, same only the size
is increasing. Okay, so let me do one thing. I'll handle in support vector. You can mention that classes are balanced or imbalanced, class weight. Okay. Okay. So here, when you do this SVC, you get an option, class weight. Yeah. Oh, sorry. You can write balanced. Okay, so when you do so, what you're telling here that, you know, if what you're doing here, remember, if there is what happens when you remember that Amazon problem that we did, there were too much of data in the positive or 5 review comment or something like that, right? So how to handle that? You want to penalize somebody who penalize the algorithm, or penalty is more when something is getting classified, something of lower class is getting classified into higher class. Understood? Okay, everybody knows the Amazon data set where you have data is more towards 5th class, I think, right? Higher classes, 4 and 5 data was more. You don't, if you accidentally penalize the algorithm, and if you try to penalize low class into high class, your algorithm penalty won't go bad, algorithm accuracy won't go bad, right? So using this technique, class weight is equal to balanced. Okay, you basically tell if some smaller class data is getting classified into higher class data, higher balanced, higher data class, okay, it will get more penalty so that the algorithm can behave that way. Understood? Right? So there are like 100 students, there are 2 classes, class A, class B. If and people get like 20 people go to class B and 80 people go to class A. If somebody from class who should go in class B is accidentally coming to class A, you penalize him more. You hit him with 2 sticks. So chances are less. And that is the whole philosophy. Chances are less that, you know, this guy will, I mean, if you measure the weightage, then this guy will be weighting high. Right, so chances are there, you know, it will go to the correct class.
So it takes in the entire data set. It can take account of.
You remember the loss function? Loss function, cost function, loss function. Right. There, what it does is, you know, when somebody get into misclassification, you are reducing the. I mean, you are reducing, you know, the impact that it is having. It has equal impact. Here, in this case, what it does, it has more impact when there is a failure by smaller class. Got it, right? That's how they balance it. Okay, so all you can try with SVC classed balanced. Let's solve some problem with this. Okay, maybe that classification thing. Take this as an assignment actually. Try to solve it with SVC. Okay, which class does it belong? What Amazon class? Just mention it. Class weight is equal to balanced. Amazon problem. Remember, we got 70% accuracy, but you know, I don't think that was a good solution. Right? You can try with SVC and class weight balanced, see what is the result. Right? This is how you handle imbalanced classes here. Okay, so 3 things important to understand. First is linearly separable data, just use the classes, I mean the kernel as linear. RBF and IBF is good. I mean, whenever you're doing image and all that, right? You'll use RBF. Like docs images, I think you try that with RBF. Okay. Anybody tried the dog thing? No. You can try this over this weekday, so that next Saturday we'll have this project session where you can show me or you can discuss whatever work you have done in this area. Okay, anything that can be related to that. I'll talk on two things. I'll talk on enterprise level data science deployment. How do you deploy a project on a scaled environment? Okay, I'll simulate in my servers, but this is, I mean, how do you write code? How do you get a problem? How do you create a data pipeline? How do you do the deployment? How do you validate your production environment? Okay, I'll talk about that aspect as well. Okay, so that I'll show you one application by deploying it in such environment, so that we understand how to do that. And we'll see one case with maybe Amazon data. If you guys are trying, great. If not, I will try that with balanced data set. Got a sense of it, right? Okay, so let's solve some image classification problem using SVC, so that we understand what we'll use. PCA with SVC is a very good combination. Okay, let's try to see that. Got a sense of, right, as what is SVM all about? What is support vectors? Okay, how do you really find out whether it is linear or RBF? Okay, so there's a face identification. This is a precedent. This is an inbuilt data set. Okay, of quite a few famous personalities. Okay. Okay, so you can write this code if you want with me. You've seen that? Okay, you try to do the same thing on dogs data. Same thing. I mean, I'm not comparing dogs with precedents, but I mean, dogs are better. So, yeah. So, yeah, but the idea is to get some idea. Okay, and the only part that, I mean, apart from this, the only thing that you might have to do with the data frame conversion from the image directly. Okay. So here it is, fetch LFW people. Fetch LFW people. Oh, today is really नाम ना बोले.
Today.
मैसेज आया तो पता चला कि.
That's why we were saying, right? You do the run. You do the run, please. One is this time, and one is during Durga Puja time.
Oh.
Yes, that's why the puja.
Okay. Oh. It will take little time, I guess.
Someone missed you.
That's how we get festival updates, right?
And you don't know that right now, Navratri.
Huh?
No, most of the people outside the core North Indian regions, they don't celebrate this Navratri. They are not even aware.
Yeah, in South Indian.
Not South, even Bengal or India. No one.
In our place, yeah. Festivals. Nice, leave it. Just give it 2 minutes. Loading up. Okay, maybe till the time it happens, I can talk about little about. So you have already downloaded.
Yeah, actually, it's all the bit of.
Nice. I thought it was already there in my system.
There's a download to different environment. It's taking time from this. This over here is running on Python 2.7. So it's downloaded this.
Oh. I think I earlier did it with minimum 3 data. Okay, so let it download. So what will you do? Let's discuss the channel. Okay, so it is a phase data. Okay, we can plot it. I think you can turn the laptop to show it. Or maybe I can just dump the. Okay, just search for here sklearn scikit.
Image. In Python, you are running that.
Oh, the face images are also there. Hello. Hi. Oh, you're there in training room. Huh? You're done? Oh, you're finished. Okay. Yeah. Okay, just let me just finish the session and meet you. Huh? Okay, so let's. Okay, so let's discuss the pipeline thing that will happen here. So, what is the first thing? First thing we need to create a data pipeline here, right? What will this data pipeline do? It will connect to the data part. Okay, and I'll discuss more about this enterprise level deployment in the next session. If you want, you can do some reading from yourself. You can just Google how to enterprise deploy so that you can bring your points also. Got it, right?
Enterprise level deployment
of data science products or machine learning products. How do you actually? We are simply writing a code, right? How do you actually put it for deployment? Then you understand, what are, like, in fact you were asking yesterday, right? How do you scale it? That okay? How do you take a decision that you will be working on this much data? So what are the resources you take? Right? What is that journey? Okay, I have a few slides to share also. So let's discuss that journey. How do you take a classroom code to a deployment code? Okay, then I'll show it how to connect. Like, you have a web page, you submit some form, and how do you actually execute a machine learning model and return that output? Got it, right? This journey, I mean, which is like final leg in, final step in connecting to the deployment. Okay, so let's discuss by the time I hope it. So what is the data size here? Let's see. The data size is here of 62 cross 47. Each image is of 62 cross 47 here. Okay, so what will be the number of features? That is around
Somewhere around
3,000 something, 3,300 something, right? So basically, on a nutshell, you're basically dealing with 3,000 features, 3,000 columns. Okay, so there are a lot of images here. Okay, and that is the scale of the data. And if you see, you are using derived columns and all that, it's gone already. If you say 2 degree also, it is already gone. What will be the feature for 2 degree? Number of features for 2 degree. For 100 columns, if you see, for 100 columns, 3 degrees 170,000. For 3,000 columns, way beyond it. You cannot do it with normal techniques. Okay, so your decision is fairly simple now. Okay, you will use SVM. Understood, right? For images, if you are using machine learning, blindfold SVM. Done. Okay, there can be competition among for smaller, cake for between other algorithms. Here there is no competition as far as machine learning is concerned. lot of years people, a lot of systems, if you see deployed, right? I mean, in your, I think, passport office or something. See, they use. I mean, somewhere in this government work, they use SVM. Somebody told me, I forgot. Something which we use, right? They use SVM as of now. Now they are this the agency who does this government work on this. No. Some government. No. Passport is CCS. NIC, National Informatics Center. There is India. So they are working on converting into deep learning. Now they use SVM for some work. Okay, I am forgetting what work they mentioned. They're now converting into deep learning to see if CNN is able to solve the problem. That's the work that is happening here. Oh, great. So let's see the sizes of the data and everything. Oh, it's a list, right? So you can have data. Okay, so you can see here, yeah. So this data is of 13,233 images. Okay, and each image is of 2914. Okay, oh, the size is lesser than what I thought. Okay, each image is of 2914. And if you want to see, oh, and actually I think I'm mistaken. Wait, faces dot images. It is 62 plus 47. Is it? 62. Same, huh? 3,000. I thought it's more than 3,000. Okay, so here this is this is flattened data, and this is data in the proper shape. Got it, right? And what are the targets here? How many targets are there? Faces. Right, you have we have 5,007 target names. Yeah, you have some 5,749 names here.
But they are just unique names.
They are unique target names, right? They have to be unique. Oh, I actually worked on minimized of data. 60 thing. I always wanted to see what is the bigger version of it. Huh?
So 13 also they are having unique
first name.
Huh?
Are these first name?
Yeah, full names. Yeah, if you want, you can read it. Right, you can see dot of them. I think it is. World presidents, huh?
4,011.
4,000?
4,011. What is the value of that?
Oh.
So 13,000 images and.
But these are your. I mean, if you want to.
Images per person. Exactly. Images per person. Yeah. New data comes in. Maybe they change this.
It will change.
New data is very less to identify because it's approximately 2 images per person. That's only 700 parameters. In 13,000 images. So the only random targets are and it could be
Right, that is the case. I mean, can't help it. That is the data. Even okay. So be it. Okay, let's see.
So no, target would be related to some row, right? Like target name would be related to some name image only, right? Then it would be within the data only, right? It's not anything from outside.
Right. So how many classes we are getting into? 5,000 classes.
5,300. That should be all within from the data.
5,360. Is it the case? Sorry. Here we shaped it. 5,749 classes. Okay, that is the problem. We will be solving that problem. Got it, right? So that is the problem. So what we expect from SVM to do? Okay, it should be able to identify among this many classes. I don't think this program will finish if I work on this data, but let me run it. Okay, let me run it. Okay, got it, right? The scale of the problem, and this is real. That is what actually that is why these guys were doing it as well. So in this component identification, you're not identifying. There are two things. One is based on your photo and a previous photo, you'll try to find a map. Is this person the same? You take your camera and you say, okay, is this person same? That is one check. And from your photo itself, you're identifying which person is this from among all the data sets. Right? What is a rudimentary way people used to do? Each photo comparison and then see how many information is this. And this is a very old age technique, right? After that, what you do now is, you have learned your model is learned for this many number of photos. You'll pass your photo and it will outcome which particular class. Right?
Kind of group.
Yeah, in your model, what will happen now? In your SVM model, it is capable of separating data of this many classes.
So that's something like nearest neighbors.
Which one? The first one?
The
similar, yeah. You can use nearest neighbors for that. But nearest neighbors also doesn't work with so much of it. Nearest neighbor don't have lot of success stories with images.
Reason?
It works with lesser number of parameters when it goes. I mean, that's what, when you talk about unstructured data, SVM was the last thing that was there to solve it. Okay, got it, right? So nearest neighbor is good for text. You have limited column text data. Okay, great, but not beyond that. Okay, so when it comes to images, this is the only guy.
Nature, that was the best thing for images, right?
Huh?
Yeah.
Otherwise, it was the best thing for images.
Right.
When we were to random state data set. Random state.
Random state, huh?
Random
State, yeah.
What is the meaning of that?
Oh, that means to randomize the data set.
No, I mean whatever value we gave.
So every time if you give, this is same as seed in NumPy.
Okay.
Got it, right? Okay, every time you give, it will generate same sequence of data.
Random state. Like some number will give only it's the same kind.
Same kind. It's similar to seed.
So it will give the same shape for particular data set.
It will give same output.
For every person.
Every person across the planet and outside it, if anybody is coding.
Actually, over here the analytics came out pretty good. Analytics came out pretty good actually.
Okay, for this data set?
Yeah.
Wow, 5,000 data, 5,000 images.
The user test size of 0.25 and dynasty.
Okay. Okay, so let's use all the things. First, it is around 3,000 columns. So first, we should use PCA plus SVM is a combination. Okay, PCA is to reduce the number of features here, because in an image, if you see, not the entire part of the image is useful, right? Corners are not useful. That is what PCA will do. PCA will remove those information. Okay, so let's use PCA now.
PCA is for derived columns.
Derived features. I mean, I used to say column because we are saying columns that time, but the generalized term would be to derive features out of it.
It will not remove features, it just
derive it. So of course, it's based on whatever passing, scalar decomposition, import PCA. And components. Okay, say we just want to use 150. Okay, 150 features here. Then SVC equal to SVC.
So this 150 is also 2,900.
150 out of derived
2,900.
29.
62, 47, 27, 29 is something. That's out of that.
Okay, and class weight balanced, right?
What is full form of RBA?
There is something I forgot. Just let's do
Radial.
my
Radial basis function.
RBF, radial basis function. You guys have the tendency to remember full forms, or?
Google.
I mean, that's why. I mean, all this upload it to Google. I always wondered in China. I don't know. I haven't seen them. You know what they do when they code. In China, huh? Is it at par with Google all this?
That it will we come to know looking at their products.
Huh? Yeah, because you know whatever you do, of course, the search engine. One is localized search engine, not localized engine. Of course, it is searching on all the data that we do is searching. Okay, but of course, it will not be in comparison to Google, right?
Most of the guys went from Google, right? Taking all this.
They will be same. So this is, I thought, you know, whatever search engine they use, it won't be of course at par with this and how they code them.
Ideally, Google is getting better because that day I was trying to complete my roommate got a iPhone and I was trying to complete the Siri with Google Assistant.
Nothing actually.
Google actually perform better.
Use Cortana is better than. Not joking. That's Microsoft's.
You have a laptop, right?
Bing is not great, yeah.
Okay, so here the next thing that will pass is balance, weight.
About Bixby is also not good, right? Samsung. And it's Lumia for like 80 years back. Cortana at that time was so much better than Google and all that stuff. Right. I don't think Google moved right.
Hey, what did I use earlier? Weight.
Class weight equal balanced.
Oh, nice. Okay, so yeah, so what do we have this, and we'll make pipeline, huh? Pipeline is the heart of the concept. I mean, otherwise code writing becomes very messy. I mean, you saw earlier it was very bug prone.
There was one more feature in which you can apply different kind of pre-processing to different columns.
Data frame mapper. Data frame mapper.
Yeah. But that doesn't support in new versions. That's deprecated.
Suppose which version?
I tried data frame mapper and this one.
No. You have to install it separately. It doesn't come directly with the library.
It's part of
Pandas. It is not yet integrated. I don't know why they are not integrating it. Maybe one point because it is not developed by Anaconda people actually.
They were the
functionalities. You'll see it maybe 1-2 months. You'll see this integrated because it is used quite a lot. I'm still not sure why. I mean, this might be one question you can ask. Why are not integrating?
Could you tell me how to download that different libraries and merge it to the
Just use pip of Anaconda. Go inside the folder where you have in Anaconda directory you have scripts directory.
Actually, you don't talk about variable. There is a conda env create. Yeah. And then once you go into that conda env activate, then you start giving commands, right? You don't have to be in that folder. Everything is within that.
Within that, that's also again.
That's the terminal.
Just, I mean, one more conda history. What do you? I mean, just a tip is the way that everybody knows it.
So even if you do depth inside that, it will be its fit,
right? No, that's there. I mean, if you make pipeline. Okay, so we'll use this make pipeline utility. Make pipeline. And pass PCA to that, SVM to that. Okay, so you have make pipeline here. Okay, so let's now get ready with the pipeline from SQL dot modern selection import train test split. Okay. Just make sure to write using the right pip. I mean, use as you was recommending conda or use pip on that folder. Just make sure that happens. Nothing else. Train test split. Okay. So here you have the images, faces, data, right? Faces, target. Right, you have the data separated out here. Okay. Then, then of course what you can do is model dot fit, right? Phoenix. X train, sorry. X train and Y train. X train and okay, so remember what we did here, around 3000 features, we just chose 150 out of it, isn't it? Using PCA. And then we have this guy here, which is doing balanced and SVC with RPF. Okay. It's supposed to give you around around 65 to 70% accuracy. 75 to 80, yeah. Okay, so of course, what we have not done, we have not passed. I mean, we didn't do grid search over here to pass what are the parameters and all that. But this is how we can actually use SVM with images and get the results.
65 accuracy.
65, I mean 75, 80, not 65, 75, 80.
That's okay. Still not good, right? In terms of image approach.
With SVM, it was. I mean, it was. That was. I mean, of course, in using images with SVM and other techniques, we never achieved good numbers. Right, but this is how you do there. This is how.
Then what do we go for it?
Deep learning, CNN. There are things which are specialized for this, right? Images, CNN, convoluted neural networks, right? So they actually, I mean, that is specialized for images.
These are libraries.
Concept, yeah, and each of call forms a library.
That would require more computational costs and more cost to deploy everything, right?
Okay, let it run, it will take some time. Okay, so PCA plus SVM, you can try this with the dogs data. Try it this time. Take this as an assignment.
Dogs data.
I shared, right? Dogs data. I shared, right? Also.
Same way.
Sure. No, the data is not there in GitHub, but it is there in. I think the link is there. It is dog versus dog breed. So dog breed, right? So you have to identify there's 120 dog breeds, I guess. Okay, do this with SVM. Okay, I think you are trying this with CNN, right? What was the accuracy got with that? 71%, right? Try first benchmark. Just see first what SVM is doing here. Okay, then we know, okay, in SVM itself we're getting 75, then whatever we did in neural network is waste, right? This is the benchmark.
No, but the difference is how do you go further? Like what other people have achieved is 95, 97 using neural nets.
Right.
So I don't know what is the best.
Right. I mean, yeah. I mean, so once you do with SVM and all that, you get this is. I mean, you're not comparing with outside world. At least you are able to solve it with this much percentage. Then you use other techniques and see how can you improve. Okay, so use this because we might dog breed identification. Any dog lover here? Huh? Oh, you're a dog lover.
These efficiency should be
higher. Yeah.
I test my own. Then lots of images I have of this. So its breed should be there, right? A Labrador will be there definitely. Most common one. White, little wooden.
So you have it here or you need it? Oh, you stay alone with?
No, I stay with friends, so I have one guy who will be permanently there too.
Oh, nice. I always wanted to do this, but
so lovely.
Then you'll enjoy, yeah.
Labrador is a big. Yeah, they are big. This big he has grown up long 1.5 years. So you got it as a pup, is it? Yeah, when he was around 3.5 months.
From where did you get it? You bought it or?
I searched it in nowhere. So there was some guy. Actually, I knew one of the guy who used to do this taking care of dogs and all. So he had his own dispensary. So he just suggested one guy. So from him only took it. It was near, I got it. It was near some Ramnagar. He had his farm, so he had some group of dogs he had kept over there.
Oh, because I went once. And that time I was not married. They said, no, we don't give it to bachelors.
Oh, is it? That guy also was saying something like that we don't give it to bachelors because they doesn't take care of it. That is what they think, that bachelors won't take care of.
That is the common perception of bachelors, right?
Exactly.
Which is not because they need attention. I mean, they need your care.
Labradors are too much attention seeker. Even if you take food, if you're eating food and if you keep them aside, they'll feel like guilty and they'll make their faces. They literally do. Like you can feel it. When the first time we got to some table, so we started having food, and he was over there lying on the corner. So that is the first time table came and we were eating the food. So he felt so bad. He wasn't. After that, he didn't eat his food only. So we literally sat on the chairs in the table and we kept his bowl near that, and then he started eating.
So we should expect you better. Better accuracy than whatever he got because he doesn't like dogs.
I was having one dog. We couldn't bite from there.
You take it bite from?
Bite means
But your dog will never bite you. They'll die of guilt if they bite their owners.
He did.
Which breed was that?
German Shepherd.
No, it was your own dog.
Yeah.
They never.
I never heard this.
He did not. I'm so much scared of dog after that. Even street dog also.
How big was it? How you handle it? How big was it? But they would never ever bite your owners because they'll feel so much of guilt. They'll be normally who is owner. Yeah, when they're very small, they don't know. But then they start giving up.
I'm so much scared.
Okay.
I don't hate you, man. Yeah, good. कोई दूसरा घुमाना तो हमें भी अच्छा लगता है।
No, stray dogs. I feed regularly stray dogs. They have fixed people, fixed person. They come at this time. They know I'll be feeding this time. They'll come then.
Yes. Don't maintain that is more difficult. With labs would be so much of hair fall and there is that thing, so much of metal.
I have seen one black color.
Black
has
Labrador.
less hair.
Black Labradors also come.
That is to just
But
stop.
no, hairs that that breed would be like specifically that dog would be having less hairs. Even the black ones have long hairs and all. But golden retriever has long hairs. Labs has less hairs comparatively to golden retrievers.
I think you didn't do the problem. At least you didn't see the data set. I think if you get rid of that fear, your algorithm will perform better. Okay. So yeah, let it happen. So I've added that dog data set here. Give it a shot. I'm still. I think he's leading the board with 71% among all the things.
That is not.
Huh? That's okay. I mean, that's in ML itself. You should get around 75. 75. You should get 75.
At least 78, 79.
Yeah, depends.
The validation accuracy.
No. Validation accuracy. I'm talking about.
So sorry. What was that? There is one more parameter, right? Which defines whether you should use.
Oh, testing accuracy, training. Testing accuracy was this. Okay, but it's a little intensive.
I think it's all done. It's done.
Huh? No, it's still that dot is happening, right?
Huh?
Any other process? Right?
This is lab, right?
This is lab.
See, I don't know what happened now. Yeah, something is happening. But how much is it? Finish.
You try model accuracy.
But yeah, they are almost similar, even for the size.
Okay, one of among us.
I thought golden retriever was just one of the.
Yeah, there is some
Category on the lab.
Now your laptop 12 GB.
No,
I had extra slot, so I added 8 GB extra.
No, AMD is not good for machine learning applications. I mean,
So what core i5 or core i7?
AMD, yeah.
i5 भी अच्छा है. मेरा भी i5 नहीं कर रही है.
But it depends on the RAM also, right? So
OS and all that.
Processor will depend. Mine is AMD actually. So 6th generation, A10. It is they told tell it equivalent to i5, but now I don't think so.
Mac Intel for last many years it is Intel.
8.
They used to be this ARM का पहले हुआ था बहुत साल पहले. At least 8-10 years it is Intel. This is not flow, right? This is yes.
What's the accuracy? What?
Got it around 65.
2 years.
What was it?
I want to got this for $50.
Yeah, it wants me to get a new dollars.
Yeah,
It wants me to get a new.
20. So this is i7. 16.
And Apple is not good for many of my work because I will install Spark, many things, right? A lot of problems are there. Open source softwares.
Seriously, because I'm planning to buy a new laptop, so I'm going for
And development work, Mac is very difficult. I find it. So not everything works well actually.
But we are like puppies in it, right? So
Linux will support good on Mac. Mac. मतलब उसका
मैं लिनक्स डालूंगा तो फायदा
वही सेम ही चीज उस पे वर्क कर सकते हो ना तो लिनक्स में फिर चाहिए उसका सेम ही तो है ना कमांड लाइन लिनक्स बेस्ड ही है
Mac terminal.
No, Mac. Oh, if you're using open source a lot, Mac, I mean, personally creates a lot of problem for me.
उसके लिए होम ब्रू वगैरह क्या क्या इंस्टॉल करना पड़ता है तो इंस्टॉलेशन का सो मच कॉम्प्लेक्स.
So I mean,
normal things that is good for mail and all that.
NPM and all those things like coding. What I do, so normal things, whatever I do, I find it good for that. Even for Java and all, environment setup, so basic things now that works. But this,
if you use open source softwares,
most of the
then
time,
it won't work. I mean, for many open source software, Mac thing, you'll get one or two options, very difficult to choose, less support. I mean, that is why I mean, because we deal with a lot of open source.
The other thing is when you got to deploy, where will you deploy? You won't be deploying on a Mac. Right? So I'll rather do, since I deploy on the Ubuntu, I'll put on the Ubuntu.
That depends on product to product or whatever the requirement is.
What they do is in our side. So we have build servers. So Mac is just used as a shell. So you just log in to all.
Let it happen anyway. It's taking a lot of time. Okay. So yeah, let's come back. Let's come back. Okay. So so next week would be, I would appreciate everybody doing this dog breed thing with LPC, SDM. Spend 3 hours. It should not take more than that. Running hours would be different. How much time it takes, but have a benchmark to that. Okay. Then choose one of these problems, and next time I'll be showing one small, very basic recommendation engine that we'll be developing. Okay, and I'll be talking about enterprise level deployment of machine learning products out there. It is like, maybe I can just brief a bit about recommendation engine, right? What is recommendation engine? Like when you go to YouTube, you see recommended videos. When you buy a product, you'll see recommended products. Right? This is all happening because of the recommendation engine that is going on in the backend. Okay, how does it work internally? In a very high level, it tries to find people of similar history that of yours, or similar features that of yours, right? And then it tries to recommend you the videos that he have watched and you have not watched.
It has nothing to do with that. They will be looking at video. It's just with other people who have seen that video. There is no learning on the video.
There is no learning on the video. Right? The data does not matter here.
The data is more on the kind of movie or whatever was.
It does not matter.
No, that is
similar videos.
No,
that is like similar videos. What he's talking about recommendation that does not depend on.
So he'll find 100 people who are like you and what videos they have watched. And based on that,
what I'm saying is how will they determine if that was for the person's life?
That is based on review history. There are two things.
Yeah. One of if I have that review history, so that will have a list of the different kinds of movies that are seen. So that will be the features. That's what I'm talking about.
Kind of.
See, I mean, in how does YouTube do it? It doesn't. I mean, not always you watch a movie fully. You take a right to that, right? So you would have liked it, but you would have not gone that extra effort. I mean, that is an extra weightage. But if you have seen a movie completely or a video completely, it means you have seen it. Okay, that means if you might have a conclusion, what was junk here, but you saw it. It was good enough to take your interest till the end, where the end may be an anticlimax, right? But it reached you. So somebody, I mean, based on your view history, and of course you might have liked some video. Based on your history, if somebody also is having the similar view patterns, okay, of course this is one part. Other thing is the profile information. Other things are also they're not considering them now. So what it tries to do, YouTube tries to recommend that person the video that he have not watched, but you have watched. The reason is, I mean, this is a YouTuber. Okay, tell me this. Suppose I think I didn't tell you. Hi-Fi moment I didn't tell you, right? So suppose his recommendation engine is a team which any e-commerce, any community company invests a lot on it. Okay, if you see Amazon's recommendation team, it is a huge team. Okay, actually it's a combination of multiple teams that works. So of course they're not fooling. I mean, they're not fools to invest so much of money in that. It is important. When you go to a shopping mall, where do you think is have you ever gone to a shopping mall to, I mean, this grocery, Hypercity or any grocery mall to buy milk? You're gone, right? But when you come out of it, what would you have bought? A lot of stuff. So what has happened over there? They have upsold you lot of things, right? So there is a upselling thing happening. You go and did you notice where is milk kept in a shopping mall, in a mall, or the essential products like dal, rice? Where are those kept? Exactly. Agar wo pehle rakh do, then nobody will go till the end. If you think they'll keep junk products in the end, will you ever buy junk products? No. Okay. They will. Oh, nice.
But even I was thinking, maybe video
You're talking about marketing.
annotations, yeah, tag hoga.
Marketing.
Right? You look at them and then
We're
you
talking
say
about
this
right
is the
now
video.
marketing.
But this is
Junk
the
items in
revelation that
front
you don't
and the
even
main
bother
items at the
about
back.
what video is about.
I'm
It's
just telling
that you
that
find
instead of
figures
technical
who are
marketing,
similar to you.
Right. I mean this is connected. Here, if you do marketing analytics, they're using this. They're using this recommendation model.
They are manually tagging things into the video description or something, right? That's what I was
Which
thinking.
kind of video it is? Music maybe ज़्यादा interest आना तो.
I thought कि maybe वो सब
Yeah, guys.
होगा. I thought
It was the previous way.
that's what I thought.
Whatever I've seen on Netflix now, gives me the option that since you watch this, we are recommending this for you.
Since you watch this, that is not. See, there are a lot of things that happen. Let me,
No, but this might be what he is saying.
No, exactly. But
by watching this, it would have figured out people
who
would have
watched
watched this. Now it will bring you closer to those people and what they did next. Right?
But there are a lot of these things you can do. But there is a high five moment in. This is a technical term there in recommendation. What is this high five? You know, right? High five, right? Yes, we did it. If somebody is buying, everybody, I think anybody is interested on this. What is this? That magic book? J.K. Rowling, she wrote it, right? Harry Potter series. Sorry. Yeah, I mean that translate. So yeah, Harry Potter series. So if you are buying a Harry Potter series book 1 and the recommendation engine is showing you book 2 to buy, if you buy it, is it a high five moment for recommendation engine developers?
No, it is not.
Because it is obvious. It is like, it's obvious somebody will buy that. You're not upselling anything. Upselling is something, if somebody is buying, you might sell raw documents. So there are a lot of things in recommendation engine, even we are trying to develop for, one of our platform here, but that is basic. But what is, compare it to the shopping mall. That's the best example. They bloody sold you chips when you went to buy milk. Right? I mean, that is the level of upselling that happens. When you map it every time, I do conscious, no, I'll not buy any other product. But what ends up, I buy, okay, I need this, I fix it. But I end up buying the full basket of stuff.
So if you go to US, most of the malls, right, towards the billing counter exit, right, they'll have magazines, they'll have your breath fresheners, chocolates, and all this stuff.
Yeah, the counter.
And while waiting, you end up buying
them. You'll start reading a magazine, and of course, you'll not finish it. You'll end up buying it. So
sometimes you feel bad also. I'm not buying, so you buy it for habit.
I don't belong to that category. Okay. Let's. So this is what is high five moment in recommendation. So you understand that a lot of things happen. Okay, what we'll be doing is a very basic stuff where it might use some other information like as the user A, user B. It will find which is the most similar user to you, and that who among the most similar user. Okay, this is your collaborative filtering algorithm actually. Okay, this is using not the product information. What you by default thing is it uses product, but for that the problem is you have to write for a movie. You have to write this movie, this product is there, and this movie is there. This is romance, this action, this fight, this. It is not possible.
I was thinking that you will do some image recognition, video ko dekhna padega ki even before like assume people have not marked it right. So first it has to be completely automated. You look at the movie, see whether it is romance or action or something. This is awesome, right? So that's the thing. Don't bother about the product. You are not looking at the product because doing it for product is very difficult.
Very difficult.
It's more like identifying the person rather than the product.
The other people. Finding people similar to you.
Yeah. This has some limitation when the data set is small. You cannot do this. That is why if you see what is that new movie channel Hotstar is hiring data scientists who are working in recommendation. Right. Then there is one more. When your product set is less and even less viewers, right? These things don't work. That is why they use this concept. People who watch this video also like this. That is what we are doing for a regular platform. Netflix, right? Okay, so I mean, there is a level of difference between Netflix. I mean, they are now trying to implement.
See, they might be printing this message, but they might be doing what you are saying.
Right. I mean, I'm talking more of a Hotstar, which is not yet that scale. Okay, now it might be, but I haven't.
Amazon Prime.
Hotstar is bigger than everything in India. वो जियो के आने के बाद
so वो सास बहू serial बहुत आता है. Okay, so but I'm talking on the recommendation perspective. So of course it hasn't grown that much. Okay, because to do this, right, you need data set. Huge data set. Then like YouTube level, they haven't done it best. Right? If you see YouTube recommendation, it's not awesome. But this is the philosophy on which they go.
They have some recommendation.
And of course, they are not investing heavily on YouTube recommendation.
Why?
I don't know. At least from the product, if you see YouTube recommendation, your Flipkart and Amazon recommendation is way better. Not Flipkart, okay, but Amazon recommendation is best.
Depends also on how much you are. I am pretty much on YouTube and I can see accounts coming
quite
out well.
But I don't know. That was my perception again. They uses this philosophy, but I think they can still do better. And they have the they have the Google's data. They could have done it better.
When I'm looking at movies and stuff, it's not that great. But when I'm looking at technical data and things, I think it's just amazing. So like when technical videos or these sort of things you're looking, what next is coming?
Gives on.
It will come properly.
ML videos, Elon Musk, get those a lot of time.
And they come properly in the order you expect.
Still, that is again my personality. I don't say that that is correct or wrong. I'm talking precisely.
Completely different story.
I'm talking maybe from more movies perspective, because the idea when I made, I didn't see it that useful. But yes, Amazon was good. But essentially, there is a lot of things that happens. Okay, but the upselling part is very important, because of how do you really measure it working, right? There is no such test and train, right? There you have to show the product, and based on how many people actually went and clicked on it, right? That is your feedback. So you can understand the turnaround time for identifying a recommendation engine is right or wrong. It takes quite a long time. So recommendation engine is like shopping malls front door products. Okay, it won't stop sell. Okay, and of course sometimes it is your information, sometimes it is environment around it. Like Navratri is there, you might be interested in buying some new clothes, right? It should have that pattern that Navratri is important for him. And the one reason why YouTube I don't find it good in YouTube ads, they don't consider your properties. Okay, being a girl, they can show a guy's wristwatch. Okay, so if you notice it, YouTube ads is more of a geographic specific. It is not taking into account who is logged in and what are his properties. So I feel there is a long way to go. If you see ad campaigning in YouTube is concerned, if ads are not using it, I really don't think any other of their functionality is using it, because ad generates revenue.
But this could be upselling also, right? Buy it for your girlfriend or boyfriend or husband.
Think of all possible things.
To depend on.
Okay, let's not get there.
Because they know you'll buy a guy's watch, right? You won't buy it.
Okay.
No answer.
Okay, so the next time you notice YouTube ads, just pay a little more attention. What are they based on? Okay, so okay, yeah. This is the test part. Your test part is finished.
I'm actually decreasing the size.
Okay, so I wanted it to be complete so that I can upload in GitHub, and next time I can show that.
So यहाँ पे कुछ verbose नहीं आता है? 5%, 10%.
You can enable it actually. Score function has it verbose thing,
but now
let it be like this. Okay, so try out few problems which you can discuss. Read a little bit more about deployments, because that is what if you get time. Okay, that is what I will be discussing next time. How to deploy machine learning products. How to deploy. Maybe I'll create a web application which in backend would be using machine learning. How to write that application. Correcting. Suppose you want to create a startup which somebody will be giving their education details. You want to predict what will happen to you after 10 years. Right? Okay, so you can do that.
This thing on recommendation engine was very eye-opening. So I always used to think the product को देखते कुछ करते.
But you can see the product को देख के then the limit.
It's impossible. That's what I used to think. कितना computing power चाहिए होगा?
And the recommendation engine is not a live computing power. I think that you asked in the morning, right? It's not a. It always runs daily. It is not like Tinder. I think I gave an example of Tinder to you guys. I gave, huh? Okay. Tinder, you guys know?
That right, left, right.
Right, left, right. So based on your, left or right, I think you're not aware of Tinder, right? Yeah. Tinder is a dating app. Good that you're not. Okay. So dating app. When you do right, what is it? Right.
Right.
See? Okay. Okay. So right is like.
Right is not
like, right? That's a muscle memory here getting in, right? Okay, right is like and left is not like, whatever is it. So it doesn't recommend you the next person photograph based on this information. Okay, because learning is not happening live over here.
So they actually Microsoft Azure was working on it.
Exactly.
To work on it.
But they failed. That's the work I know. One of my friend was in that team.
Like Azure, they had some machine learning algorithm or something algorithms they were trying to apply on it to
do the live
learning the next one.
Yeah.
But then somehow it failed.
No, my friend was in that team, which actually prototyped and it failed actually. Two reasons. Why it is happening in the cloud. The response time was too much. Second, the amount of computation that it incurred was too much. I mean, the cost that Tinder had to pay for this was way beyond what they were planning. Two reasons it failed. That is why cloud-based machine learning, there are great things that can happen, but there are things that cannot happen. Okay.
When cloud-based response time, if you consider.
Yeah, because it is going two ways, from your to system to Tinder system to Amazon system. Right? Sorry, Azure system, right? Microsystem learning in it's too much of a route that is happening over there, not suited for things like this.
So YouTube recommendation engine has been open source with TensorFlow.
When did it happen?
It's been there for a while.
Can we see the code?
Something called Google Brain.
Google Brain is the team behind TensorFlow.
So what they use is something called candidate generation. Probably what you were explaining. I think that's the technical term.
The technical term for what I explained is collaborative filtering. This is I think derivative of it.
Candidate generation, which takes as input users watch history and using collaborative filtering selects videos in range of 100.
Right. So this is the baseline algorithm. Okay, collaborative filtering. It's a very basic algorithm. Okay, if you want, you can implement it also in Python. Okay, but that is what it is. Okay, so the few things I think that you can use is Google profiling function. That might be because of Google's you sign in Google, right? I mean your information, whatever the information they carry of yours, right? They won't share it. Even though YouTube is Google's company, I think I don't know what will happen between them, but it doesn't use Google's information. Okay, you can check it out. That's the information I got it. I of course didn't do a lot of extensive research in that area what they use it, but okay, this is the story around it.
I think what it says is the way they have done it such a way is so that the collaborative filtering can pick up viral videos right away. So more than it being good for you, they want the viral videos.
Various way to be more viral.
Because I think the way it happens is their revenue model is different, right? So many people they spend day in day hours to make videos, right? It's their job, and then they are uploaded and people are watching them, right? उसके ऊपर advertisement आता है.
That one for the trending section.
Huh?
Yes, section for trending.
So even when you just log in, I think it comes up.
So the code is open source?
It says so, but this is only one. I think then there is another paper in 2017 December also.
Oh.
Google padenge. But I think it is Google Brain.
Google Brain is of course the team behind TensorFlow. So I mean they are Andrew Ng was the head of that team.
Before that, Google had built a system known as Signals. But it is Brain that employs the technique known as. So it uses unsupervised learning.
Right.
So it falls in line with. So you wonder why I never searched it before. I had to come to your class, and then in today's discussion. Up until now, I was just thinking कि videos को कई codex streaming करके उसके बाद deep learning से classify करते हैं.
It's not that complex. Cannot do that such complex.
Yeah, that's
on
what I was
on that
How
scale.
can we even do that?
Yeah, on that scale, you cannot do that complex thing. If you're doing something at huge scale, it has to be simple. Right? I mean, that is one thing that we'll be discussing. I mean, the thing is, the simple things are more productizable. I mean, if you have a complex thing, it is good for prototype only. You'll never see the day of sunlight. Okay, so you have to think simple. Convert your complex thing into simple thing, then the deployment will be easier to do. Okay, guys, let's wrap it up here. Okay, our training is not done. I'll upload it so that we have a benchmark thing. Your